I'm David Bray. I'm from the Hartree Centre, and we from a group that specialises in chemistry and materials modelling. For those, let's see if I can get this work. Right. For those who don't know what the Hartree Centre is, we are part of the Science and Technology Facilities Council. We're based at Daresbury Laboratories, which is not far away from Manchester in Cheshire. And STFC mostly focuses on large-scale facilities. So you may, it's particularly useful if you want to use some large equipment for materials measurement. But we're a little bit different in the sense that we focus on digital technologies. So we specialize in supercomputing, data science, AI, and machine learning, cloud computing, and quantum technologies. And all of our projects are challenge-led and focused on industry. And so that means the problems we try to solve are always motivated by a challenge that we find that industry is coming across. So we work with a lot of UK companies trying to overcome their digital challenges. In terms of the area that I've been asked to talk about today in soft matter, well, soft matter covers a range of areas, including colloids and surfactants, complex liquids, polymers, granular materials, liquid crystals, and sort of biological and life sciences. And you'll find them in all sorts of industry sectors. So this is just a subselection of the kind of sectors that we work with, in particular the home personal care, the materials, pharmaceutical and agrochemical. Yeah, they're ambiguous in that way. But given the time I've got available today, I wanted to just focus down on one section of soft matter that's industry relevant, and that's in the formulated products. So the formulated product industry is worth about $1,000 billion per year. Formulations typically are fairly complex, so they can contain up to over 20 chemicals, and that makes them quite challenged to keep them in spec. At Hartree Centre, I've just listed 4 examples of the current trends we're finding from the industry that is leading to R&D development at the moment. So there's a big drive in sustainable products and ingredient replacement. So a lot of the formulations that exist today contain ingredients that, particularly petrochemical derived ingredients, that need to be replaced. So there's a big drive to reformulate products. Additionally, we've got to look at reduction in energy usage. That might be found in manufacture or transport. So it might mean you need to replace your feedstocks to reduce transport or change the manufacturing process. The third example I've got here is pretty standard. Everyone wants to understand their products better. So they want to either how to improve their performance or increase their lifetime stability. And the final one I have here is a relatively recent use case, which is personalized formulation. So an example of this you can imagine is skins creams, which you would tailor to individuals' skin type. And so you need to do customized formulations, and that means you might need to come up with unique formulations for that. So all of these drivers mean that the R&D cycle is considerably shorter now. And what we're finding is companies want to know whether digital technologies can actually help them speed up that R&D process. So I put here a challenge question that quite often comes up. So really this is basically looking at how can I use digital technologies such as modeling and simulation to speed up the R&D cycle. And this is really about how can we in-house these technologies into companies. So this is the question. I'm going to try and show you some of the work we're doing into trying to enable that. For the example I've got to show you in this talk, we're going to look at surfactant formulations, surfactant-based formulations. So with surfactants, they're often used for cleaning or as dispersants and modifying agents. They self-assemble into aggregates, and depending on the morphology, that can change the properties of the formulation. So, for example, depending on the structures they form, the viscosity of the final formulation can be very different. Their big problem at the moment is a lot of them, the current surfactants that are used are petrochemical derived. And so there's a big move to try and move towards more sustainable replacements. And that means that a lot of the knowledge that's been built up over the years needs to be replaced for these new surfactants. Right, in terms of modeling simulations, so the first thing we have to do is choose an appropriate approach. Because we're interested in morphological properties of surfactants, that drives us towards the more mesoscale techniques. So we want to be able to see the molecular level structure, so that's see individual molecules and how they self-assemble. But we need to see for the size of the structures they form, we need to typically use a mesoscale approach. What that means is we go down a coarse grain route, which means that we take atomistic structures and then we bead them up into chemical groups. And each of those beads have to capture the unique chemical properties. So I've shown 3 examples, or 1 of an oil and 2 of surfactants, to show the typical form of the coarse grain models we will take. And you'll notice they're color coded. So each of those captures some of the chemical properties that are based on the real chemistries, but the potentials that we use in our force fields are simplified. So it's a very simplified model. What we try and do with our modeling is we always try to think of what is it that the lab-based chemist would want to know and try and do the computational equivalent. So we've been over time developing a suite of virtual experiments to look at various properties. So typically things that are important in surfactant chemistry is the critical micelle concentration and the morphological properties and phase behavior that they take on, and then also looking at surface interactions. In more complex formulations, then you've got to worry about the interaction of surfactants with other chemicals, such as polymers or additives. And so we want to increase the complexity of the simulation in order to study the interactions that are going beyond between them, and also looking at the transport properties. So this is just a sub list of some of the things we've looked at as a team at Hartree Centre. So for my first example, I wanted to show you the equivalent in the modeling to the experimental picture that you might look at if you want to study microstructure, surfactant microstructure. So at the top, I have a penetration scan, which shows the different phases that the surfactants will take at various concentrations. So depending on the light scattering, you can identify the different morphological phases that surfactants form. Below that, the animation that just ran was the equivalent simulation for that, and that actually represents the bottom slice of that penetration scan. So you can see directly the phases using the simulations, whereas you have to infer those in the experiment. On the top right, I have a cryo-TM image showing worm-like micelles. Those are the black squiggly lines that are shown there. And in the simulation, you can investigate those directly by looking at their morphology. So we've just got an image showing the spear-to-rod transition and identifying the concentration of surfactant in which that occurs. But more often we want to understand full phase diagrams. So a formulator would actually want to understand the phase diagram that a particular surfactant would form in order so they can formulate at the correct place. So we can do that with modeling. and simulation techniques we have available. So the blue images are snapshots taken from the final state of various simulations which have increasing concentration going from left to right. I've also done sort of cartoon images to show you what the morphology of the surfactant packing is based on those images, just to make it a little clearer for you. Looking at the shape and the morphology properties of each of those aggregate structures, you can actually identify the phase state that this simulation is showing. And what we have on the right here is comparison between simulation and experiment. And what the simulation is doing is, if you look at the experimental plots, those are the real phase diagrams that have been made using experiments. The red line is the cut across that phase diagram that we're doing with the simulations. And you can see that with our simulation data, we can reasonably accurately get at the right concentrations the correct phase state that the surfactants have taken. Another thing that is quite important to the experimentalist is the critical micelle concentration. So in the middle, we have a diagram of various experimental techniques used to calculate the CMC. In this case, it's for SDS. But surrounding this, I've shown basically how we can use modeling and simulation to predict this. So we take a series of simulations of surfactants, various concentrations, and we can use that to backtrack out the CMC measure. So the bottom equation is just the equation you can use, the equation that you can use in order to derive the CMC if you know the concentration of free surfactant and concentration and the total concentration. So does it work? Well, I've got a table up on the left here, which shows the comparison between what we get from the experiment and what we get from the simulation. And you can see there's a reasonable agreement between the CMC and the simulation and the experiment. On the right, I've shown it for an ionic surfactant. So these are the family of SLES surfactants. And you can see, again, you get a fairly good agreement between the predicted and the experimental CMC. So this is great. So for very pure monodispersed surfactants, we can reproduce the critical micelle concentration. But in reality, most real surfactants are a blend, so they contain multiple substances. So what about mixtures? Can we predict those? Well, it turns out we can use a more complicated equation to relate a mixture of surfactants and the CMC it will get. So if you solve that equation, you can come up with a theory which will then predict the critical micelle concentration of a mixture based on the CMCs of the pure surfactants. So the right images is just showing the solid fit, just shows that we can reproduce using the theory the behavior of the CMC as predicted from the simulations. So what we're showing here is the free monomer concentration. There's an example here, but this will then can then go into the equations and then predict the critical micelle concentration. So that's very nice for mixtures, but often you get a commercial grade surfactant that claims it's SLES 2, but its CMC is much lower than this. So if you look on the right image here, you can see that the pure SLES 2 is predicted to be 1.17 grams per litre, but the commercial grade SLES 2 is actually down at 0.28. And we can use our theories to then say, well, what's the cause that causes the commercial grade to be less than? Is it due to polydispersity in the SLES surfactants? Is it due to a small amount of unsulfonated alcohol, or is it due to salt that's included in there? So once you have this theory, you can use this to then hypothesize why there are differences between your commercial grade and what it claims it is. And that is useful if you've got a problem with things being out of spec due to your selection. Another thing that we're interested in is pH sensitivity of certain surfactants. So here we have two surfactants that are pH sensitive. This means that they take different forms depending on the pH of the system. So the salt form and an acid form. And we can use our simulations to predict behavior of the co-surfactants at the given pHs. So if we run the simulation, what I have on the left here is a system that's run a blend. So we take surfactants, they're randomly dispersed in the box, and then we allow them to aggregate. And over time, they form different morphologies. And those morphologies change as time increases in the simulation. So we're able to predict into the future the final state of the system. So if you start them at random, they form spherical micelles. And as the spherical micelles grow, they elongate to form rods. And those rods then eventually branch to form a branch structure in this case. In terms of why we would want to know this, well, it allows us to predict the experimental behaviors. So say you're interested in viscosity and you want to ensure that you get a high viscosity build in your formulation, and you want to know what's the best pH to formulate up and the blend of surfactant and co-surfactant, then you can use the simulation morphologies to predict the viscosity, the behavior of viscosity, and because morphology relates quite nicely in simulations to viscosity. So on the right, we have an experiment that was made by Croda, the company called Croda, and then on the left is our predictions based on the simulations. And what we were able to do was identify the region in which we thought there was going to be a high viscosity build. That's where you get a rod-like or lightly branched micelles. And we also able to identify a region in the top left corner where there were highly branched surfactant morphologies. And that's where you don't want to formulate, because if it's highly branched, then you get a very unstable formulation. It's likely to crash out. So we can also say where not to formulate. And so with this, it's good enough to eliminate 50% of the experiments you would have to do, because we can basically target the experimentalist into the region that we think is most likely to give them the viscosity build. So I've been through a few examples on surfactant chemistries, but a lot of these ideas can be translated to the other areas of soft matter. What I wanted to finish on was basically to tell you what we found modeling simulation can do. So it's very useful for validating an experimental result, particularly say if something's gone wrong, then we can use modeling and simulation to basically investigate possible causes for that. It's also very good for filling in data that's missing from the experiments, so we can add additional data before going and doing the experiment. Like what was mentioned in previous talks, you do get fairly accurate results from the models, but they do need good parameters. So we have to match the chemistries reasonably well in order to get differences. Because it's coarse-grained model, there's simplifications in there. And so in order to be able to tell the difference, to make it highly bespoke, this is particularly important, for example, if you've got molecular structures which are variations or isomers of each other, then we need to make sure the forcibles are sufficiently well specified that we can tell the difference between them. Additionally, we often need to carefully rationalize the formulation, because there's a lot in the real formulation, there's a lot of competing interactions that are going on. So in order to make sense of what's in your system, it needs careful thought on the experimental techniques. So it's no different, I guess, to experiments, simulations. Strategy that we use has to be thought of in the same way. But if those are both well thought, well designed, then what simulation can offer you is a good way to do some material discovery, because you can trial lots and lots of surfactant molecular architectures in silico first before going into the lab. And it's often, depending on the experimental technique, it can be a lot faster to run the simulation than it is to do the experiment. So thank you for listening to me. And